So, in the previous episode, I assembled the craft for the first time and I laser leveled it in to find out the correct length for the Kevlar ropes. And then I was all set for the first tests. So I took it to my playground and I mounted the propellers and let's see how that went. So, what can I tell you? I made the mandatory mistake of mixing up the rotational direction of some of the propulsion units. So the two back propulsion units are swapped, so they're sucking themselves down towards the ground. And then you say, oh, it's just to switch any two wires to the motors. Yeah, it is, but it's 38 motors and everything is soldered, so it took me a while. But anyway, I fixed it, and here's the next flight attempt. So I really dislike finding out the properties of a new aircraft with a NASA controller, because the throttle on the NASA controller is not about being proportional to the RPM of the motors. It's about how fast you want to ascend or descend, and the center position is supposed to be altitude hold. So when I centered it, it just dropped like a stone, and that was scary. Anywho, let's try that again with a new adjusted the basic gain settings, and I increased them because that's what's suggested in the NASA manual. So let's see how that works. As you could see, it took off in a nice manner, keeping itself level and nice. And I was prepared for the down drop when I centered the throttle, so I could compensate and keep the craft in the air. And then you get a very important clue. You can see that the craft starts turning, and then it goes like a rodeo horse, and quite uncontrollable. So the next test, I increased the basic gains, and especially the yaw gain, because I thought that will help it to not start yawing. And let's see what happens. So I'm thinking the flight controller gets really confused if you bounce the craft down into the ground and up again, which is evident in the video. And also I'm thinking that increasing the basic gains is not solving the problem I'm experiencing. Yeah, and I did break the chair. I think it broke in a soft manner, so I think it would have helped save your back, and that's good. My next step now is to rebuild the chair and switch out the NASA flight controller to a KK 2.1 board, which is a flight controller I'm used to, and I think it's a better tool to find out the dynamics of this craft. So that's the next clip. the first few hops are just nerve-wracking, but the KK board gives you better control over this sensitive phase where you're just trying to get the craft off the ground without crashing it. After a while I can fly fairly level, but it continues to yaw, and you can hear some of the motors are revving up, and that's me giving full opposite rudder, trying to counteract the yaw motion, but it just doesn't happen. So what I do is I put in washers under some of the motors to tilt them in the opposite direction to cancel out the yaw motion, just to find out what's going on.
Jaha, då är det fjärde testet nu då. Nu har jag återställt alla 12 motorer till neutralläget för att kompensera för en medjursvridning den hade förra vändan jag var här. Men jag rättade också till linlängden innan jag gjorde alla de här justeringarna, och det verkar vara linlängden som gjorde att den drog i höger varv. Ni ska se nu hur det funkar.
When I finally managed to balance out the multirotor, it is evident, isn't it, that the propulsion system of this multirotor does not produce any useful amount of reaction torque. And that is just so mind-boggling and weird. So it took me a long time to figure out how come and what to do about it. And this is how I'm thinking. I think it's useful to think about torque reaction in a multirotor context as two separate things. The first one is the continuous torque reaction, which is generated by the propeller's inefficiency, because when it spins, it propels the air downwards, but it also accelerates the air in a spiraling motion. So the counterforce of that spiraling motion is the continuous counteraction, counter torque. And the other half of the puzzle is the impulse reaction torque, which comes from accelerating or deaccelerating the rotating assembly of the system, and that would be the propeller and perhaps some sort of propeller mount and the rotating part of the electric motor. Let's start to think about the continuous torque reaction in this system. I have low pitch propellers that are efficient, and that's bad if you want to have a significant amount of torque reaction. They are good at producing static thrust, which is what you want to have when you are hovering, as opposed to a higher pitch propeller, which would be poor to produce static thrust, because part of the airfoil will be stalling while it's static, and it will gain efficiency once it's moving through the air. So that's bad in this context. And also I have 19 propellers spinning in the same direction on each propulsion unit, and spinning in the same direction means that the tip of the blades are actually meeting each other in opposite direction, so that will probably cancel out some of the spiraling motion in the air underneath, also reducing torque reaction. And to make things even worse, the outer motors are positioned in such a way that the tip of the blade sweeps over the aluminum structure, and I think some of the air adheres to the structure, also cancelling out some of the continuous torque reaction. So that's the continuous torque reaction being unusually small. And then we have the impulse reaction torque of the system. And it is low because I use so light propellers. They are 17-inch, but they only weigh 22 grams each, compared to this 15-inch propeller that weighs 45 grams, just as a reference. And also the rotating part of the electric motor that I've chosen, the Elite, is very light. It has strong magnets and thin backing iron, so it's expensive, but it has a high power to weight ratio compared to this motor, which has solid backing iron and weaker magnets. So it's the budget version, but it weighs a lot more and is less powerful than the Elite motors. So that makes up for a low impulse torque. And also I can add that the mass of these blades are rather centered. They're so thin and slender out here, so that also makes it easier for the motor to accelerate and deaccelerate the propeller, but you get less reaction torque out of the system. And it's almost mind-boggling to think about that the combined swept area of these 76 propellers sweep 10 square meters, and the combined mass of the propellers is less than 1.8 kilos. So that tells you something about the difficulties of obtaining a lot of reaction torque, impulse reaction torque in the system. So what's the cure for this? Well, after thinking a lot about it, I figured out that if you were to mount the motors slightly tilted in the direction that the reaction torque should have produced a yaw motion in, that probably would do it. You would not have a snappy torque reaction, but you would have forceful, continuous torque reaction to control the craft, which should work. So for a short moment I thought, wow, I'm a genius. And then I Googled it, and of course it's a well-known solution. I didn't know that. You can even buy small plastic spacers specifically to tilt your motors. But I, of course, opted for 3D printing new motor mounts. But I started out with adding spacers under each motor, tilting them in the correct direction. So I remounted the all 76 motors with 2 washers, which gives a motor tilt of 2 degrees in the desired direction. And this is what happened the first flight with that setup. So isn't it amazing that a bunch of washers could turn this failure into a success? It's very docile in yaw because it's the motors are tilted so just slightly. So I printed out new motor mounts for all the motors, so they're tilting 6 degrees instead. And that still you don't have any snappy yaw movement, but you have definite control over yaw. So it's forceful, but it's not like a high impulse factor on it. But now I can fly it with ease. So let's check that out. And now, when the craft is fully flyable, it's just irresistible to try with the NASA controller again. So I remounted the NASA controller and did several test flights. The one I'm about to show you is the most recent one. So finally up in the air with the NASA controller, it could maintain altitude, but it feels twitchy and non-intuitive in the controls. So I opted to switch back to the KK board. And the next step is to make a version with 5 flight controllers coupled to 5 receivers, which is controlled by 5 transmitters, which is coupled to a custom-made joystick. Let's take a look at the build and the first flight with this Penta system. After 10 minutes flight, I have a cell resting voltage of 3.8 volts, which is good. It's a good storage voltage, and it also provides me with a adequate reserve of about 1 to 2 minutes flying time before I'm down to 80% depth of discharge. So I'm very pleased with that. And the next test will be trying to take off with one flight controller turned off. So you're 16 motors short, but I think it will work. And if it does, I will try to switch off one flight controller in mid-air and see what happens. But that is for the next episode. So thank you for watching, and thank you.